Very excited to be at our final session here of CISE. Hope you all have been having a good day. And we'll just get right into it. So we have two final speakers today, two final invited speakers. And so first up, we'll have Bob Wilson.
Okay, so thank you for having me. Thanks to the organizers. This has been a fantastic conference. I've had a really wonderful time. Thanks to everyone for making it happen, especially the ones on the organizing committee who actually did the work. I know it's always unevenly distributed who actually does it, but whoever did the work, I really appreciate it. So thank you. Thank you for doing that. So I'm going to talk about the explore-exploit dilemma, and it's an interesting audience to introduce this to, right? I thought I'd try a different way of introducing it. So whenever I introduce the explore-exploit dilemma, I actually face the explore-exploit dilemma. Should I use the same tired restaurant example I've used before? Do you explore this ravioli or exploit this pizza? Or do I try and come up with some new way of introducing the explore-exploit dilemma, like this meta explore-exploit dilemma? So that's what I'm doing. That's all you're getting on the intro to the explore-exploit dilemma, except for this statement. I love this quote from Peter Whittle in 1979, describing the explore-exploit dilemma as the ultimate instrument of intellectual sabotage. It's so hard that it distracted Alan Turing during World War II from trying to crack the Enigma code, and they thought if they drop it over Germany, it would distract their scientists just as much. Something very like Monty Python about this, right? I really love this. I love this quote. It's a hard computational problem, right? From a computational perspective, it's hard. And so what we've been trying to understand is how do people solve this hard computational problem, right? So we and others have proposed sort of two strategies for how you might do this. One we call directed exploration. Everybody has their own words for this, right? I think this is something that maybe a society for CISE could maybe agree. We need a like they have in chemistry, right? They have a whole committee for nomenclature. I feel like maybe we need that in this field. We call it directed exploration. That's like information seeking, driving exploration by choice, and then random exploration where you're random and it drives it by chance. So what I'm going to do with this talk is just talk about how these, some behavioral proof that these things exist. This is pretty old work. We'll talk about some properties of directed and random exploration, and then present a kind of unifying account of how you might get these things, and then I'll talk about my midlife crisis at the end. So we will look forward to that, right? That's the clickbait. So directed and random exploration exists. So this is old work now, but for those who've not seen this task, this is the task that I've exploited my entire career. And it's based on the restaurant example, or at least the intuition is from the restaurant example. Suppose you're making this pizza pasta choice, and it's the last meal at this restaurant. You're leaving town, the restaurant's closing down. In that case, you should just exploit what you know to be good, right? And then let's have you make the same decision, but in the context where you're going to be there for the long term. You're coming back to the restaurant, right? And so now you should explore. And so if I can just measure your difference in behavior between those two conditions, I can tell something about how you explore and how you exploit, right? And so we turn this into a bandits task, because we're banditsologists. And then it looks like this. You play a slot machine, you see a reward. In reality, they come from some Gaussian distribution. There's one option that's better. We tell them it's better, but they don't know it, right? They don't know which one is better. So if you're playing the task, this is all you see is the outcomes from the trials. And we keep everything on screen, so there's no working memory demand here. And then one of the key tricks to the Horizon task is we start off by forcing them to choose the two options in a pattern of our choosing. So in this case, I forced you to choose 3 options of this blue one and 1 option of the red one. And what those forced trials allow us to do is really precisely control what information people have before they make a free choice between the 2 options. And then the trick is, what do they do on that free choice as a function of how many more free choices they're going to have, right? So here they have 1 choice, it's the end of the game. Now they have 6 choices. This is the long horizon condition, and they should be exploring, right? So the key is going to be, how does this first trial behavior change as a function of the horizon, right? So we can quantify behavior across trials using a kind of choice curve. So we can just say, how often do they choose this option on the left, which I'm going to refer to as the more informative option. Nomenclature is a problem here. It's the more informative option in that you have less information about it already. Getting another sample from this is going to give you more information, right? You can formalize that in a Bayesian sense. You can also just say you get twice as many samples if you sample this, right? You go from 1 to 2. On the other side, you go from 3 to 4, right? So that's only a 33% increase. So how often they choose that high info option is a function of the difference in mean reward between the two options. And in Horizon 1, you get sort of a classic kind of sigmoidal choice curve here. As the mean of one option goes up, they're more likely to choose it. But they're not perfect, right? They're making some mistakes here, right? Choosing the low value option sometimes. But then the trick is, what do they do when you have a long time horizon? And when you have a long time horizon, they're more informative. They're more information seeking, right? They are biased towards choosing that informative option. If you look at the slope of that choice curve, it also gets a bit flatter, kind of like they're being a bit more random as well, right? So we can formalize this with a very simple descriptive model where we say people choose based on a decision variable that's based on the difference in expected rewards, plus some information bonus that's going to characterize directed exploration, a bias towards the unknown option, and then some random decision noise. Plug this into a model. This will give you a choice curve that looks like this, has this lovely geometric interpretation that the information bonus is the offset, and the I love it. You can fit these things with just a ruler, right? And the noise is related to the slope of this curve, right? So when I fit this model, I see the information bonus and the noise go up with horizon. That's what I take as proof that there's two types of exploration, or these two types of exploration exist, and we can measure them in human behavior, right? If you don't believe me, there's a literature going back to 1979 that involves several other people in this room, including Michael Frank, who I don't know if he's stuck around for this talk, but gave a really nice demonstration of directed exploration in 2009, right? So that's the existence of these two things. Let's just sort of blaze through a few properties of them, right? So we saw a great talk yesterday, the last talk, I think, yesterday, on how these two kinds of exploration depend on uncertainty. You can show that here in the horizon task by just messing with the number of force trials I give you, right? Do I give you lots of force trials, not so many, or somewhere in between? That allows me to set up 6 different information conditions now, right? A set where you've got different amounts of information, right? 1 versus 2, 1 versus 3, and 2 versus 3, and a set where you've got equal information, but your total uncertainty is different. And now I can, inspired by some of the work we saw yesterday, I can just plot how does the information bonus vary as a function of the difference in uncertainty between the two options, where I'm computing difference in uncertainty based on an ideal observer model. And then same thing for random exploration. And I see this really nice linear increase linear kind of increase with directed exploration with difference in uncertainty, and random exploration with total uncertainty. And this graph includes one of my favorite data points, probably my favorite single data point of all time, which is this one on the right here. The most noisy decision in this task, the most random decision in this task, is where you're choosing between 2 bandits, where you've seen one outcome from each, and you're trying to maximize your reward. This is the easiest decision you could make. You just have to pick the number that's highest. That's the one they're worst at. I love that data point. I absolutely love that data point. It's my favorite data point of all science that I've done. Pale blue dot be damned. Okay. Okay, so that's nice. Got this uncertainty stuff, corroborates other things that have been found. We can also see that these two types of exploration are dissociable. And there are lots of ways to do this with sort of factor analyses and things like this. A lot of people have been involved. Caroline is the current member of the lab, sort of shouldering this burden. And what I'm going to do is just very quickly show a bunch of different results for a bunch of different populations and experiments, showing you that random and directed exploration just change differently. So here is the results I've shown you so far in college-age students, 18 to 30. Here's what happens when you do it in younger kids. Directed exploration changes, right? The horizon effect seems to go away. for directed exploration, but not for random exploration. It's the same in kids as it is in adults. If you go into older age groups, directed exploration goes down, random exploration goes down. You get some similar kind of pattern in schizophrenics. Directed exploration goes down, random exploration largely stays the same. And then if we zap the frontal pole, at least in one study, we can get rid of directed exploration, but not random exploration. So lots of evidence that these things are dissociable, right? At least at the level of individual difference, and in this TMS experiment at the level of the brain. There's lots of other results out there. This is a very incomplete list of other papers that have shown things that correlate with directed but not random, things that correlate with random but not directed. I think it's probably meaningful that the thing on the bottom there's fewer examples of, right, than the thing on the top. We can maybe talk about that later. Last thing I'm going to say about the properties of directed and random exploration is really random. This is kind of gets philosophical, right, when you say, is it really random? Is it really random? And what do I mean by random? Well, one thing I could mean by random is, I've got this model where anything that's not difference in reward and not information bonus, I just say is noise, right? And then I say that noise increases with horizon. But are they really modulating their noise with horizon? Are they really more random in horizon 6 than horizon 1? Or is it just they're doing something deterministic that's based on the stimulus, but it's not related to rewards or information, right? It's something else deterministic. They're distracted maybe by something deterministic in the task. So perhaps we're just missing something from the model. So one way to get at this question is just to have them make the same decision twice, right? So set them up with 2 games, and I've got the same thing twice because it's two games, separated by about 10 minutes. This is work done by my first graduate student, C.U. Wang, so really smart guy now, NIMH. And we separated these things by about 10 minutes. You can't tell, when you play the game, you really can't tell that you're getting the exact same sequence of forced trials and the exact same outcomes for those first 4 trials. The rest of the game plays out completely randomly. But I'm giving you the same decision twice, separated by 10 minutes. And then what I can test is, do you do the same thing both times, right? If you do the same thing both times and you do that consistently, then that's an indication that your behavior is a deterministic function of this stimulus, right? Whereas if you're random, you're going to not agree with yourself, right? There's lots of ways I can analyze this. A very simple way is to say, how often do I agree with myself? Call this the agreement index, or p-agree, as a function of the difference in reward between those two. And if I'm purely deterministically driven by the external world, I agree with myself always, right? No matter what the reward is. If I am random, I agree with myself sort of based on how driven by the reward I was, right? So if the reward difference is very big, then I'll agree with myself more just because I tend to choose the high value option, right? If the reward difference is 0, then I agree with myself much less. And then I can just, on this graph, plot what humans do. And this is what they do in Horizon 6. They're pretty much entirely random in Horizon 6. They're not entirely random in Horizon 1, right? It really seems like the noise that gets modulated with Horizon is random noise. So I really love this. CIU's got a whole paper on this currently in revision where he models this, he estimates these types of noises. Really beautiful stuff. So random exploration really seems to be random. But the story doesn't quite end there, because we can also ask, is random exploration random even on the very first trial, the very first time you do it? Or is it just like you're learning something? And so this wonderful student, Alfie, who came to me as a master's student at Georgia Tech, came to me at the start of the summer saying, I want to fit neural network models to things. And I was like, okay, here's some things to fit neural network models, one of which is the first trial of the Horizon task, right, from about 1,000 people. And what she did is she just fit a bunch of neural network models and said, can we predict Horizon 6 behavior any better or any worse than Horizon 1? And here's the result for one of those models. You predict Horizon 6 on the very first trial with about 73% accuracy with these fancy neural networks, and Horizon 1 with about 83. You just can't predict Horizon 6 as well. It's more random. Do that for a bunch of models. She fit all the models. And there's some sample size issues here. Some of these models get kind of big, but across all these models, people are random. People are more random in Horizon 6 than Horizon 1 by any behavioral measure that we can come up with. Okay. I don't know how I'm doing for time. My 10 minutes. Oh, 10 minutes. We got tons of time. Okay, I'm G'd up. Okay, so I don't know why I'm looking at this. I can't see anything. I'm looking over here as though I can see it, and all I see is like a faint white line. Okay, so I'm going to come up with a unifying account, and this is the idea that maybe you can get all of these effects from just a simple idea of mental simulation. People solve these things by mentally simulating, and I remember the exact moment when I sort of realized that you could do this incredible talk from Ben Van Roy at RLDM in 2015, which is 10 years ago now. I remember his talk's still online, actually, if you want to go and see it. It just like blew me away because I realized that this thing solves everything. They call it deep exploration. I think they called it that because Ian Osband wanted a job at DeepMind. He's now at OpenAI, so studying open exploration or something, I'm not sure. But anyway, so there we go. So the idea is really simple. It's just mental simulation. So the idea is I'm going to mentally simulate exploring. I'm going to figure out how much I would earn in my mental simulation. I'm going to mentally simulate exploiting, and then I'll repeat that a bunch of times, right? N times, where n's going to be small, like 2, right? A few times. And then I just pick the option that, on average, in my simulations is best, right? Sounds reasonable. The key is I'm going to simulate plausible futures based on the information I have about the 2 options, right? So let's just kind of play this out and imagine a sort of optimistic simulation in an exploration case. So what if this 50 that I see from the explore choice here was a unlucky draw from a high mean distribution? That means it's optimistic case. So in my mind, I kind of think, what if this really, the true distribution was like this? This red one is higher than this blue one, right? Like centered at 75. Well, then I would mentally simulate a good outcome, right? So this is like I explore and it's good. And now the trick comes, I'm not just simulating the bandit, I'm also simulating myself. What would I do if I saw a good outcome? Well, I'd probably stick with it. And if I do that, I'd continue, and if I'm assuming an optimistic case, then I'd keep getting good rewards and I'd keep sticking, and then I would evaluate this simulation by its average payoff per trial, which is about 76 points in this case, right? And then I could do the same thing for exploiting and take the difference between these two, and this first sort of pair of simulations favors exploration by about 17 points in this case. But then I could do a pessimistic simulation. I could say, what if this 50 was a lucky draw from a low mean distribution, right? What if it's really bad? So now I explore mentally, and it's a bad outcome, but now I'm simulating myself, right? My own choice now is not to stick, it's to switch. My simulated choice is to switch to the exploit option, right? I've got a bad outcome, not going to stick with that, I'll switch. And so I play out the simulation to the end of the game, and now in my mental simulation, I only pay the cost of the exploration once, right? And that's the key asymmetry that makes the explore-exploit dilemma interesting and hard, right? Like, if you explore and it's bad, you only pay that once, you switch back to what was good, right? You explore and it's good, oh, now you've found something you can stick with forever, and you get the good outcome forever, right? That's a dynamic that's going to allow this model to create directed exploration, right? To exhibit directed exploration. So if I do this in this case, right, I get a second sample that favors exploitation, but not by very much, right? It favors exploitation by not very much. Then I can just accumulate these differences in values over time, right? Kind of in a DDM type way. So the first sample was plus 17 for exploration, then it was minus 5 for exploitation, then maybe it's plus 20 for exploration, minus something for exploitation, whatever, right? I sort of get this drifting, diffusing decision variable, right? That's moving over time, and then I can have some sort of decision rule at the end that's either stop after n simulations or stop when it crosses some sort of threshold. Either way, qualitatively, it doesn't make a difference for what I'm going to talk about. And that's it. And from this, you get everything. You get everything that I know about a directed and random exploration. You get, first of all, the existence of random exploration. You get random behavior because the simulations are random, right? That's not that impressive. You get directed exploration because the simulations are deep, right? And because you're simulating what you would do in that situation, right? So I simulate a good outcome and I stick with it. I simulate a bad outcome and I don't stick with it, right? If I do that, and I need 2 simulations to really do it, I will get directed exploration as well, right? It also accounts for the effect of horizon on both directed and random exploration because the simulations go out to the time horizon, so the results are horizon dependent. That just comes for free. The effect of uncertainty comes for free. And then it predicts this new thing. It predicts that you actually have a trade-off between the 2 things, at least in some tasks, where the more samples that you have, the more directed you become. So the information bonus is predicted to get bigger the more samples you have. Kind of a tricky argument as to exactly why. But the argument for why random exploration should decrease with the number of samples makes total sense. The more things you're averaging over, the less noisy the average is, right? And so you predict a trade-off. If I plot now directed versus random, I should get this negative line, right? Downside is in the horizon task, the effect's too small to see. So we actually designed a new task, a different task, that I'm not going to go into in the interest of time, but I can if you want afterwards, where you can make this trade-off really big, right? So if I just look at the scale here, this scale on this y-axis goes from 0 to 10. Here it goes from 0 to 50, right? So I've had a 10x increase in my sort of information bonus. And so what we can do is using this new task, we can ask, do we see this trade-off in behavior? And all I have to do is estimate directed exploration for each subject and random exploration for each subject, which I can do. And then I plot them against each other and I find this really strong negative correlation that survives all sorts of model assumptions. And you can even get it within subjects as well. I won't talk too much about that. But then we can start to, we're modelers, we like to fit all the things, and we can start to take the things a bit too far because we can say, well, how many simulations do you have, right? So about 17% of people are best fit with 1 simulation, then 37 by 2, some by 3, some by 4. I can get a histogram of this. The number of samples in this model is a continuous variable, actually. So you get this histogram. And then you can really push it too far because you can say, well, people who simulate more should have longer reaction times. And you see that across the population. And then you can really push it too far and say, well, what's the slope of that line? Because that's how fast as mental simulation is, right? It's 50 milliseconds per sample, which is like really, ooh, that's a sort of suggestive number, right? The history of cognitive psychology, right? Like working memory, pre-play and hippocampus, right? Wouldn't that be great if that wasn't overstepping what I should be doing? So overall, we've got this model, right? This mental simulation model can account for everything, and that's a big claim, right? But it can account for a lot of the qualitative properties for free, right? You can get all these. The problem is you can get all these properties from other models, right? And quantitatively as well. But I really like this sort of parsimonious explanation that if you can just mentally simulate, right, and it doesn't necessarily, we're not making strong assumptions about how you do that. It could just be you have a neural network that can generate samples for you, right, in a kind of, just a recurrent way. But it can explain everything. So that's kind of fun. And then I thought I would just end with a midlife crisis, which is, is this all just cognitive computational behaviorism? So what do I mean by that? In that we've got this really nice cognitive model here of mental simulation. Like Tolman would love this. Like, all the cognitive people would love this, right? It's a real nice cognitive model. And then I'm testing it with this behaviorist choice data. It's just a bunch of button presses, right? Like, what am I doing as a cognitive scientist? Like, really absorbing the lessons of Skinner, right? Like, Skinner would love our methods, might not like our models. What are people actually thinking when they do these things? So why don't we just ask them? So this is a new line of research in the lab of just asking people to think aloud while they make these decisions. It's got this really rich history in cognitive science going back nearly 100 years. Using these think aloud protocols to really probe what people are doing. And just to give you a hint of it, I'm only going to show you raw data here, just to give you a hint of how powerful this is. Consider this decision, this chess-making decision. Look at this. It's a castling decision. If you're a computational behaviorist, that is all the information you have to go on about the cognitive process underlying this. Maybe you have millions of those trials, right? You got it from Lee Chess, 1 minute, okay. Maybe you don't, right? But you've got the choice, you've got the response time. But if you watch chess streamers, you've actually got what they're thinking at the same time. So I just want to show you, this is Hikaru Nakamura, one of the best chess players in the world, talking about this very decision.
I can also trade and take, and if it takes, I take. If it takes, queen e2, queen h4, g3, knight g3, check, c6, queen b7, knight h1, king there. I don't know what's going on. I'm just going to castle. I don't want things to
Isn't that incredible? Mental simulation and model free, right? Like he was like, screw this, like cognitive effort. It's incredible, right? It's incredible, the detail that you get from one choice there. So we're going on that. We're doing this with the Horizon task. Hanbo has done a ton of work with risky decision making. I'm going to end it there because I'm out of time. I'll just thank everyone from the lab and our funders. And then I'll leave you with some quotes from the Think Aloud from the Horizon task. Okay, thanks.
Hey, great talk. This is super amazing. I guess I'm just wondering how you square the Think Aloud with the 50 milliseconds per sample.
Yeah, I know. Isn't that an interesting question? Yeah. I think there's two issues there. I mean, one question is the reaction time analysis kind of overstepping what I should be doing? Another is, what kind of decision are we getting at when we have this pre-play that is fast like this? What is that cognitively, right? Like, you know, is that a decision that we as a human would describe as a reflexive decision, right? Or is it something that's like planning and cognitive, right? So I'm just asking questions back to you here, right? The other aspect is you go back in the Think Aloud literature, a lot of the behavioral effects that they see, because a big question is, does making people think aloud change the behavior, right? And it really depends, right? But they had this model, Simon and Erickson have this lovely sort of model where they say what you can think about for free is stuff that's in working memory. And the minute you're not talking about stuff that's in working memory, you behave differently. And so in that view, all that you're doing when you ask people to think aloud is slowing down the process, not necessarily changing the process. But it is a big question, right? Like, they didn't know about hippocampal sweeps, right? Although they did know about, 37 milliseconds for working memory. So, I can't square it is the honest answer. But, that's not to say we shouldn't try, right?
So I'm trying to square the individual differences with directed and undirected with the final model.
Mm-hmm.
It seems like the parameter that you showed in the final model is number of simulations. Seems like number of simulations should affect both the amount of directed and undirected exploration. And so I wonder if you are reconsidering the idea that these two things are actually unyoked in across participants, that you get like different measures of
so I have a whole slide on this, right? So there's a couple of things you could think about. On this slide, I talk about sort of the policy really matters, right? So the simulation policy really matters. If you do not have a smart simulation policy that's got some kind of like win, stay, lose, shift dynamics, then you don't get directed exploration, right? So things like schizophrenia or prefrontal damage or whatever potentially could knock out the simulation policy part of the simulation, right? And you could get a dissociation. The other thing is that all of that dissociation work is in the horizon task, where the predicted trade-off between these two things is really, really small, right? So essentially unobservable. And there are lots of other factors. And then the final thing is, even in the model, this mental simulation model, there's a bunch of other parameters that come in that could allow you to change the noise separately from the information seeking. So I agree, it's potentially a problem, but it's something we can kind of, the parameters allow you to work around it.
Yeah, that's really cool. I was wondering, so if I'm playing a game like chess, if I'm trying to think forward, I find that I'm trying to sample future possibilities, but they're highly correlated. You know, the one I'm sampling now is based off the one I was just sampling, and often I'll miss an entire separate pathway. Is there some way you can take that account in your modeling? I feel like it might almost be, rather than separate independent samples, it's like a tree structure where one branches off from the other.
Yeah, so so in sort of reinforcement learning and cleverer planning algorithms, right, they will cache the samples, cache the simulations, return back to them. And certainly you can do that. We have not done that, partly in the horizon task and in the other task. It's such a simple task that I'm not sure you would get a huge benefit from that. The other issue is just, it's such a hidden process. And this is one of the things that pushed me towards Think Aloud, right? It's such a hidden process that to get at it from behavior is pretty tricky. Yeah. Exactly. And some of the earlier work we've seen today, right, in the sequential exploration tasks, right, we're trying to get to a goal state, or some of the eye tracking tasks where maybe you could get at what they're planning from eye tracking. So I think there are ways to do it. Yeah, we've not done that in this stuff, but yeah.
Let's thank Bob. Okay, and our ultimate talk, Jackie Gottlieb.
Ultimate talk, yes. I hope. Thank you. I hope you have the energy for one less bit of, few less bits, curiosity, and it's going to be hard to top Bob for entertainment value, and I say that with admiration. I have to. All right. So, okay, so I will talk about meta-level control of attention and learning. And I want to start with a bit of philosophy. So when we walk, so Bob mentioned the Skinnerian behaviorist paradigm. And we don't use that word very much these days, but we all very much live in the shadow of that way of thinking. So when you walk into a psychology or neuroscience lab, you see a setup somewhat like this. There's a screen, a participant sits in front of the screen. There is a stimulus presented on the screen, and then the participant does something based on that stimulus. And you would say, of course, this is how we do it. This is how we always did it. How else could we do it? It's matter of fact. But if you think about it, this very setup packs some very, expresses a very strong philosophical stance about what behavior and what the brain does. The first assumption, some very powerful assumptions, and they're very related, that information is exogenous, is fed to the brain, is given to the brain by an actor that's external to the brain, and the participant doesn't have control over the information. And it follows from this that neural processing is bottom up. It's the story starts with the stimulus, enters the eye, and only after that, the only thing we need to do is decide what to do with the information that's given to us. This is very, very unrealistic, and it misses, maybe by design, most of the complexities of what our brains are for. And our brains are for dealing with realistic environments like this one, where there is no stimulus. What is the stimulus in this room? For some of you, hopefully it's me, but for others, it's your iPhone. For others, might be the weather outside. For others, might be something you're dreaming about, something inside your mind. So, information hides in plain sight. which means that it must be selected by us, which means that processing has to be very heavily top-down. So the story has to start from somewhere inside the brain where we make a decision to orient our eyes or our attention to some location on the screen, and only then do we have the stimulus that we can start to process in a feed-forward fashion. Okay, this idea immediately brings up the difficult question of computational rationality, because information is practically infinite. Our environments are much more complex than we will ever master, probably, and our resources are very limited. So whatever this top-down controller does is must implement some sort of computational rationality, some sort of a decision of how to engage limited resources so that we end up, so that we do something useful and we can survive. Okay, so my talk today would be about this decision to engage, and I will describe 2 lines of work, one in relation to attention and the other that's newer in the lab in relation to learning. Okay, so let's look at attention first. So as many of you know, there are tens and hundreds and thousands of studies of attention. They have focused on visual areas, posterior areas that have usually retinotopic representations. Neurons respond to stimuli at specific locations that have specific features. And as you might know, there are many studies documenting how attention affects those feature-selected responses. There's increasing gain, reduced variability, a whole bunch of effects, behavioral and neural. All of these studies, though, talk about how attention affects something after it is deployed, right? So in all these experiments, participants attend to something, and then there's a bottom-up stimulus, and you see how the response to that something are affected. But the question we need to grapple with is, how did someone come to attend to that location to begin with? Okay, the go-to answer in our field has been that it has something to do with the rewards of the task. So in other words, you have a lot of stimuli. If something promises to give you more reward, you're going to attend more to it. And there have been many experiments done with this idea in mind in a particular visual area, and the results are surprisingly messy, right? It seems like a very obvious hypothesis, and yet many people find conflicting results. Sometimes you get enhancement by reward, sometimes you get suppression by reward. Anyway, the field is spinning around its tail, and there's no resolution. All right, so we have been working in the lab on this for quite a number of years. And our studies are motivated by this reasoning that when we attend to something, we select a stimulus. A stimulus gives us information. Information is a reduction of uncertainty. And therefore, a decision to attend to something must express a decision to reduce uncertainty by discriminating that stimulus. And as I said, we did a whole number of papers on this that we looked at different aspects of this. But today I will talk to you about this model of this uncertainty-based attention control that I've been working on with Massimo Silvetti, who's a computational psychiatrist in Rome. And Mattias Horan is a super talented student, doctor by now, surgeon who did his PhD at UCL and now is off doing neurosurgery. All right, so I will cut. I won't go into detail because there's too much data to talk about. So I'll just give you the bottom line of how this model works, how we think this circuit works. So we think that attention control is sort of a meta-level control where we have in this model, we have a visual map that simulates a retinotopic visual area. In our case, we looked at the parietal cortex. Neurons in that area have spatial receptive fields, and the activity is enhanced by attention. We know that. And our postulate is that these enhancements are triggered by a boost of norepinephrine, so a generalized boost of neuromodulation. The specific, we do think norepinephrine is a good candidate based on the literature, but it could be other modulators as well. This is not important. What is important is the mechanism that regulates how much norepinephrine there is in the system. And we postulate that that regulation comes from an executive circuit that includes the anterior cingulate cortex, together with dopamine afferents that are shown here in red, and norepinephrine that is shown in orange. This circuit controls the level of norepinephrine, which controls attentional enhancement. And what's important is that it decides how much norepinephrine to put out based on a cost-benefit computation. So it does a traditional optimization. It maximizes the utility function, which looks like this. So the rates of reward, it wants the rates of reward that are signaled by dopamine to maximize the immediate and discounted future rewards. And what's important and what's special here is that it also wants to minimize the boost cost, the amount of effort, and that is the boost of norepinephrine. So the boost of norepinephrine is a cost to the system. The system tries to achieve the maximal rate of reward possible with as little norepinephrine as possible. Okay, so So then what this circuit implies is that norepinephrine, which again is equivalent to the level of attentional enhancement, is a cost to the system. So that's the opposite of a reward, is a sort of mental effort that you put in order to obtain a reward. And let me just show you how much better this model does at predicting neural responses. So I will show you, these are the firing rates that Matthias recorded in a task in the lateral intraparietal area. So let me describe you the task a little bit. What we have here is we have a monkey sitting. He's planning to look at a stimulus, which is in the visual receptive field of our parietal neuron. And he looks at that stimulus before making a decision. He has, at the end of the trial, has to decide A or B, and if he's correct, he gets a reward. So he plans to look at the stimulus that will help him make the decision. And we give that in two contexts. In one context, that's a trial block. The monkey is uncertain about the decision. So when monkey starts the trial, it could be A or could be B. It's 50-50. He doesn't know. He has uncertainty to begin with. And he knows that after he looks at the stimulus, he will resolve that uncertainty because the stimulus will tell him for sure if it's A or B. So he expects to gain information from that stimulus. In other blocks, though, we simply block the correct alternative. So for 50 trials, monkey comes in, it's always A. We force the monkey to look at the stimulus, but in this case, the stimulus is redundant. So the stimulus is reward relevant because if the monkey doesn't look at it, he doesn't get his reward. So reward expectation is there, but information gain is zero because the stimulus is redundant. So what you see here, these are how neurons, independent, okay, so what you see here are the average firing rates of a bunch of neurons in two monkeys. The thin traces are two different monkeys. You can see that responses are enhanced if the monkey has uncertainty. Again, the sensory motor rewards are equated. If the monkey has uncertainty, though, there is enhancement of the visual response. The monkey expects to gain information. Orthogonally of uncertainty, we also modulate the reward size, and that you can see here on the x-axis. In any uncertainty block, the monkey could expect a large reward if he gets it correct, or a small reward, and we tell him in advance. So on the x-axis is the reward expectation, and the amazing thing is that the neurons respond more if the rewards are smaller, if it's a small reward rather than a large reward. Okay, so now this is obviously a bit of a difficult response pattern to explain with reward expectation alone. But what we did is we took the reinforcement meta-learner, the model that Massimo developed, we fit the model to the monkey's behavior, and then we looked in the visual map of the model to see what the visual responses look like. So we did not fit the model to the neural responses, but lo and behold, the model generated those responses that fit the monkeys, and they even fit individual differences between monkeys in very interesting ways. And just to hammer this point, This is what a traditional reinforcement learning model would do. This, again, it fits behavior, and the behavior fit is actually pretty good if you have a traditional reinforcement model. But if you look on the visual map, the visual modulations it produces are totally off because they only depend on rewards. So you can see that clearly the activity is higher for the larger reward because that's the salient reward cue. Also, you can see that the activity is a bit higher. This is actually significant for low uncertainty blocks. And why that is because those blocks are a bit easier. The monkey makes the same choice, is highly habitual. They're at ceiling. They never make a mistake. When there is uncertainty, the monkeys make a few mistakes. So reward expectation is on average lower, and the trials are more difficult, right? So, okay, so we do think that this is quite strong evidence that what we have here, so when we think about how does the brain generate those attentional modulations, it is sort of, those reflect the recruitment of sort of attentional effort, a cognitive cost that the brain decides to pay if it gets enough reward for paying that cost. And this is a good model. Anyway, so this is a biologically plausible model that makes predictions that we verified, and we continue to verify those predictions. Okay, so now I'd like to switch gears and talk about decisions to learn, right? So this is an experiment that I'm doing in collaboration with my colleague Vincent Ferreira, a very talented Leo, a very talented graduate student, and Greg Jensen, who's a cognitive scientist, recently moved to Reed College. Okay, so learning, like attention, acquires information or acquires knowledge. There are important differences, though. So learning is much more effortful. Attention is, shifts several times a second. Learning requires sustained attention. It evolves on much longer time scales. And also learning requires updating internal representations. Attention, you just sample, you don't really change your beliefs or about the distribution and so on. Okay, and a related question that we will address in this study is what are the inputs to this ACC circuit? So the story that I told you, we assume that ACC monitors some sort of dopamine or reward rates, and we talked about how that influences visual areas. But now let's think about what is it exactly that ACC monitors? Again, in our model, in the test that I've just shown you, the signal to boost norepinephrine was simply the reward rates. So if the monkey enters a high uncertainty context, where all of a sudden he's choosing a stimulus, but he gets it wrong because it has high uncertainty, that's a signal to say, hey, you got to do better, pay more attention to that information because that increases the reward rates. We also used the model. We also extracted from the stream of rewards. The model looked at reward volatility, and we used that in a separate experiment to estimate the uncertainty of the environment, and we generated intrinsic motivation, so non-instrumental information demand that I didn't show you. Okay, so what about learning? What are control signals for learning? And some of you know that reward volatility has also been shown to produce modulations of learning rates. But here I want to ask the question a little bit differently. So to look at a different aspect of this problem. So let's look again at a natural environment. And let's think about certain things you might want to learn about this scene. So you might want to ask let's say you're a kid and you're trying to figure out what's going on this street. So the various questions you might ask. You might ask, well, I see this traffic light here, it's red and green. How does that relate to the traffic? So you might look at this scene and investigate, and that would be good. But you could also, how does it relate to the traffic? That would turn out to be a good question. You learn something by investigating it. But in natural environment, there are actually a lot more random and nonsensical questions than there are learnable questions. So you could ask, how does the traffic light relate to the pedestrian clothes? It's a perfectly valid question, but you wouldn't be very smart to focus too much on that question because you won't get very much. So ideally, a control signal for learning would be such that it distinguishing learnable from unlearnable questions and tell you do not learn, do not focus on these questions. This is important both for computational rationality, so we don't labor in vain, and also to prevent fictitious inferences, because you could imagine all kinds of explanations and correlations in objectively random events, and obviously we don't want that. But there's a huge problem here, and that is there's a chicken and egg problem, because how do you know if there is a structure before you learn to discover the structure, right? So this is really an unfair problem to pose to the brain, right? It's unfair that we have that problem because we cannot really solve it perfectly. And unsurprisingly, the little behavioral evidence there isn't a lot of work on this question, but the little behavioral evidence there is here is mixed. So some studies say yes. So for example, infants seem to attend longer to structured versus random artificial grammars, which is good. Also, there's a study in pigeons that shows that pigeons seem to prefer structures of stimuli that have predictable versus random associations to reward. On the other hand, a study that I did with Pierre-Yves Boudet and Alex Ten, we looked at people, we gave people different learning activities where they could engage with an activity, and 3 out of 4 had a learnable rule, but the 4th one was totally random, and people were totally focused, allocated a lot of time on that random task because it was really annoying, at the expense of learning the other learnable tasks, right? And related to this, we know that there's a lot of illusion of control. There are many situations in which people believe or imagine they can control or they find structure in random events. All right. So so with Vince and Leo, we looked at this in a transitive inference task that they have worked on for a long time, and we chose it because it's a high-level cognitive task that requires inferring an internal model of a stimulus sequence. So this task was very simple. On every trial, the monkey started by achieving fixation. He got 2 images. He had to choose one, and he either got a reward or he got no reward. And some images, the critical manipulation is that the images could come from one of 2 lists. Some images came from this from a set that was learnable, meaning that there was a true objective order. So for example, if you get A and B, you get rewarded for choosing A, but not B. If you get B and D, you get rewarded for choosing B, but not D. Other interleaved, though, with those learnable stimuli, there were pairs that were drawn from an unlearnable list that did not have any order. So here, for example, we just arbitrarily give them labels. You have B versus D, but your reward is random and equal whether you choose B versus D. And so again, those lists, just like in natural environments, were interleaved and unsignaled. So it was up to the monkeys if they detected there was any difference between the lists. And we also equated their reward probabilities, and we did so dynamically so that as the monkeys learned the learnable list, their reward probability on that list increased, but we matched the reward probability on the unlearnable list to be dynamically matched every 5 trials. So they're really identical. Okay, so what we find is this monkeys learn the learnable list really well. I mean, this replicates years of research. You can see that, so here in the training phase, we give them the adjacent pairs. So we train them with A, B, B, C, C, D, D, E. At trial 400, we abruptly introduce all the other pairs, and the monkeys spontaneously make the inference that if A is better than B and B is better than C, the first time they see A and C, they know that A is better than C. So this is a hallmark of model-based, and there's a lot of previous work that supports that monkeys use internal representations. The surprise here was that on the unlearnable lists, monkeys also choose as if there is an order. So those are, what I'm showing you there is 2 example lists. The example on the left, there was really strong ordering. Monkeys liked the stimulus we call A, and disliked E. Like you can see very clear, there's a very clear preference. Again, transfers as if there's transitive inference. On the right, I'm showing you another session, another list introduced on another day. Also significant ordering, but weaker, right? So, okay, so we quantified this using it's a fairly simple measure. It was a model-based measure, but fairly simple. So simply a z-score, we gave every stimulus a z-score that indicated how much it was chosen by the monkey. So if you plot the z-scores as a function of the actual rank of the stimulus for the learnable list, we see very consistently above baseline slope. And then if you do the same for interleaved learnable list, on some sessions, you have the unlearnable list has much shallower slope, which means that the monkeys detected it's not ordered. But on other sessions, it's much steeper slope. Indicating that the monkeys thought they were very similar. So what we're interested is in the difference in slopes, because that tells us to what extent the monkeys detected the difference. All right, so ACC neurons, we looked at the neurons and we analyzed them for two factors. So whether they detect learnability, the learnable from unlearnable, whether they respond to reward, and whether they respond to the interaction. And the answer is yes to all of them. So you can see that about a third of our neurons detect learnability. Some respond more for learnable, others respond more for unlearnable. A lot of the neurons, more than a third, respond to rewards, and that's very well documented for ACC. When the reward is delivered, many neurons respond more if there's a reward. Many more, at least half respond more if there's no reward. That's also very well known. The interesting thing here is that we can also decode those two quantities. The interesting thing here is that learnability is encoded before the reward delivery. So here what you see, those little blips on the x-axis, the first blip is when the monkey makes the choice. At time 2000, he gets the reward. So there's a long period there. So you can see that the learnability is encoded before the choice, but the signal increases after the choice. So in the post-choice epoch and after the reward, consistent with some sort of a monitoring signal. So it's not just the stimuli, it's some sort of monitoring and then the reward decoding only happens later after the reward. And importantly, there's an interaction. So in the sense that how neurons respond to reward, neurons respond more to reward in a learnable versus unlearnable list. So you can see here, for example, if you look at the red traces, dark red is very well separated from pale red. So dark red responds to a reward. Pale is response to no reward on a learnable list. There's really a huge signal there. But reward versus no reward on unlearnable list is much smaller differentiation. And you can see the same happens here on the bottom. There are neurons that respond more to no reward versus reward, but they show the same thing, that this differentiation is stronger for learnable versus unlearnable lists. Okay, so, and finally, the most important thing is that these learnability responses predict the monkey's behavior on a session-by-session basis. So if you look at on the x-axis, I'm plotting the fraction of neuron variance that is explained by learnability, so how strong that learnability signal is. On the y-axis, we're plotting how different the monkey's behavior is on the two lists. And you can see that when the monkeys can differentiate more, neurons tell you more about learnability. And the same is for this is the variance explained by the interaction. We have a similar correlation. If you just look at the variance explained by the reward itself without learnability, then there is no correlation. And here is just illustrating the same thing, just doing a median split. If you have in purple the sessions where the monkey really differentiates, he knows one is not learnable, the neurons encode learnability very robustly. If the monkey doesn't differentiate, you can see there's almost no signal in ACC. And the same for the interaction. And then again, the reward-related response is not affected. Okay, so this is, so this is broadly consistent with our model. I think this opens up a lot of questions that we plan to pursue. One of the more interesting questions concerns what is that signal of learnability? How does how does the brain compute it? So I've shown you that in our instantiations, when we use the model to explain attention, we use reward rates and reward volatility, and it's very clear how the brain can compute and monitor and extract that. But in our study here, as I told you, these are the reward rates for learnable and unlearnable. I told you we matched them, and we really did match them very precisely. So the reward rates are identical, the reward volatility is identical. Another quantity that we have proposed before that the brain can monitor is learning progress, which is the derivative, the increase in reward rates. And you see that that also will not work here because that increase is also identical. So none of these traditional ideas will work. We need to get even more sophisticated. What are candidates? Controllability is something that Ali Reza mentioned this morning, something like the mutual information between your action and the reward, how much your action controls the reward. It's possible that perhaps at the beginning of the monkey's experience, they got more of a sense of controllability by chance, and then that continued on. Perhaps there's something about sensing of am I building an internal model of the task? Is my task representation evolving in a certain way? And another thing that's very likely to be important are the prior assumptions. So based on their previous experience, the monkeys may have assumed that things are learnable or not. So anyway, these are great questions that we're very interested in. And the bottom line is that we really need a sort of meta-level controller to account for computational rationality. There are a lot of mathematical accounts of computational rationality out there. And I just want to say that this is a biologically plausible architecture that makes detailed predictions about neural responses. And we have evidence that some of the predictions are correct. And so we really look forward to answer all these other questions with it. Thank you very much.
Great, thank you. We have time for maybe one or two questions.
I have to ask this, but do you believe we can make genuinely random decisions? Like, given your paradigm in the more realistic setting, like, are we more likely to make decisions or base that attention control just randomly? Like, because it sounds like it's not. I just kind of want to hear what you would think about random decision making.
Yeah, I don't think we can make very random decisions. I mean, people are, notoriously difficult if you try to make a random decision. That's actually hard. You have to work at it. And I think, so this is just opinion. But I think that even when we say that when attention is random, when you just view a scene, you don't have a task. People call it random attention. I don't think it's random attention. I think it's driven by whatever it is you're thinking of. So it's just call it random because we don't know what the task is that you're doing. But I don't think, so I think attention is always sort of internally generated.
I do have a second question. Attentional control, like, and this isn't so if I'm saying something a little bit off, but there are I guess mental diagnoses that have attentional control. Would that then, would that enter into your model at all, or is this just more like a normative account?
Yeah, no, absolutely. I mean, I would think, but I just don't know. And this is a great area of investigation because clearly there can be a lot of things that can go wrong in this control process, right? Estimating uncertainty is difficult. Knowing where to attend. There's a lot of evidence that, for example, when you put people in tasks where you just explain, I can explain the problem to you, this is the uncertainty you have, those are the predictors you have, decide where to look. And there can be a situation in which if you thought about it the correct way, you could get 100% accuracy. But we find people don't do that at all, whether they attend or press a button or whatever. So we think that there's a lot of learning that has to be involved, right? In some situations, you see attention being very efficient, going reproducible. And I think that that doesn't get derived by reasoning, that gets derived by some learning, trial and error learning process. So anyway, this is all to say that it's a complex circuit. A lot can go wrong, and yeah, it can be related to emotion. All of that is in there.
Yeah, a brilliant talk. Thank
Yeah.
you.
Thank you. Yeah.
So I was curious about the like non-learnable condition, like what the behavior, like the animal's behavior look like. Like, do they show like choice history effects where they like, will like make the same choice repeatedly, or that there's any evidence that they're doing some sort of like hypothesis testing or sort of like sticking with some idea, even if
Yeah. That's a very good question, and we haven't done that. We haven't done serial trial. And it would be very interesting in light of that finding that on unlearnable list, the response to the reward is dampened. So that would suggest that the learning on the next trial might also be less. So yes, that would be, but we haven't done. We need to do the modeling for that.
Okay, let's thank Jackie for a wonderful talk.
Thank you.
Now Matt is gonna close us out.
Well, I have the, I guess, easy job of saying thank you. This has been, fantastic. This is my dream for a conference, to wake up in the morning in my own bed, drink my coffee, and come have people like fly in from all over the place to present their research that I'm really excited about. So I hope that you've all enjoyed this as much as I had. And now I guess we walk through the people we have to thank for this. First of all, I guess everybody who came and attended, whether you presented or just came and interacted. It's been a great community, and I think the discourse both during the talks, at the poster sessions, and sort of between events has been really fantastic. I hope everybody else has experienced that as well. And of course, to our speakers, both the invited speakers and contributed talks, like I said, I couldn't have asked for a better setup and a better program. Really a diverse array of methods going after sort of the same set of questions, which has been really fun to see. And on that note, the people that put together our program, our organizers who put in a lot of hard work, Romy, Joe, Ohad, and Haley, at the low level, we're doing a lot of the work and grinding away, deserve a lot of thanks for putting this whole thing together. And Jackie and Tally provided nice, support in knowing how to do things. And then I just am here to, say thanks to everyone. Yes, but we should all thank our organizers who really put in a lot of hard work to make this happen. And yeah. And of course, we also had some sponsors, and we did our organizers were able to make this happen on a pretty small budget, but we, are much indebted to both Brown University and University of Birmingham for contributing funds that allowed us to, have all of our vegan meals and, to have some coverage for our speakers, and to, generally have it feel, like a nice conference. And yeah, so thank you to Brown, thank you to Birmingham. Also, in particular at Brown, the administrative staff has been really, really helpful in making this happen. And in particular, Pat Mancieri really managed to put everything together and avoid Romy or I having a heart attack, which I think, maybe just barely avoided, but avoided nonetheless. And Rosanna Cabral and Kathy Gerlach also provided a ton of support for this conference. And then finally, thanks to all of you for coming and, contributing to this, wonderful conference. Now you have one more thing to do, which is a survey. Actually, you have two more things to do, which is this survey and then return your badges, apparently.
Also, thanks to Jay for all the pictures.
Oh, I forgot to put on the big picture that this that this picture is thanks to Jay. Sorry. But yes, please do the survey. Or do you have to say more?
I wanted to say something. Sorry.
Yes, come on in. Yeah.
Just very briefly that, I think some of you are repeat attendees, and I think that there's just a lot of enthusiasm and excitement and curiosity about this topic of curiosity. So we continue to try to get a regular conference going. We're still working on the format. We're considering several options. But in any case, there probably will be a repeat of this in next year. And so stay in touch. We will get in touch with you, and I hope you stay just as enthusiastic as you were today. Thank you.